Okay, we're on example 6 in our functions and graph topic. We've had a look at inverse functions and modulus functions, and we're going to have a look at odd and even functions. Interesting idea, an odd function and an even function. So what is that all about? Are all functions odd or even, just like all numbers are odd and even? The answer to that is no. Odd functions and even functions are specific types of functions, and some functions are neither odd nor even. So let's have some of the definitions of an even function. Is that if you were to substitute, if you were given a function and you were to substitute in a negative number, you would get the same answer as if you were to substitute in the positive version of that. So if you were to put in -2 into a function, you would get the same answer as if you put in +2. Now, what does that mean? It means that for any graph that you're trying to draw, if you think about it, if I'm saying that the y coordinate is the same for, say, 2 and -2, we're saying you get the same y coordinate. Then if you repeat that for every set of numbers, if you were to say 3 gives you the same answer as -3, x equals -3, then effectively what we've got, say there's -1 and 1, what you've got is symmetry. So every y value is the same for positive and negative values of x. So you're going to end up with some kind of symmetrical function. Okay, so they're symmetrical about the y-axis because they've got matching y coordinates on either side of the y-axis. Okay, and interestingly, polynomial even functions contain only even powers of x, and that's another little sign that you're going to get an even function. So example 6 says prove that the function f of x equals x to the 4 minus 2x squared plus 5 is an even function. So there's a clue there. Remember that a constant term technically is an even power because it's x to the power 0, and 0 is in the set of even numbers. So a proof, remember, requires 3 steps. First of all, ideally, you want to establish what you're looking for. Okay, so we can say here that the f of x, or the function, is even if, and we're going to use this definition here, if f of -x equals f of x. Always write that out. Always convince yourself of the logical argument here. The function is even if f of -x is equal to f of x. So what we want to do is, we've already got our definition for f of x. We don't want to put in 2 and -2 or 5 and -5 because they're only individual examples. What we want to do is a kind of algebraic proof. So what we want to do is, for the function, we know the function f of x is x to the 4 minus 2x squared plus 5. We want to put in -x, which means that we can rewrite our function, and anywhere where x goes, we're going to put in -x. And if we simplify these terms that have got the powers here, -x to the power 4 is going to be positive x to the power 4, because every even function, every even power has to be positive. Okay, squared terms are always positive, 4 terms, 6 terms are always positive. And the same goes with -x squared has to be positive x squared. Plus 5, and you'll notice that what we end up with, the f of -x, is x to the 4 minus 2x squared plus 5, which is exactly what x, up here. So what we've done is we've shown that f of -x is the same as f of x. And because we started off with the supposition that if f of -x equals f of x and the function is even, we can finish off our wonderful conclusion by saying as f of -x equals f of x, then the function is even. Okay, any less storytelling is just not acceptable. So first of all, state the conditions that we're looking for, then go through the algebraic process of showing that the condition is true, and then take a moment to write down your conclusion that because we have proven the case, then we can declare the function is even. Okay, so you can have a go at having a look at those ones there, and we'll have a look at odd functions in example 7.